Buonasera e benvenuti a GraphRoma. E anche questo mese, come ormai di consuetudine, andiamo online con un nuovo webinar. E prima di passare al piatto forte della serata, il talk appunto dell'evento, come di consuetudine partirò con una breve introduzione del Meetup. E nulla, quindi farò questa breve introduzione per poi passare la parola al nostro speaker di oggi. Il nostro meetup GraphRoma, immagino siate qui per questo, è organizzato da queste 4 persone. Io sono quello a sinistra, come vedete ci sono Enrico, Piero e Gabriele che aiutano a organizzare l'evento. E questo meetup è basato su dati connessi, in particolare queste sono alcune delle tematiche che affrontiamo e cerchiamo di farlo ogni mese e affrontando vari aspetti dei grafi o comunque reti o dati connessi, link e data. GraphRoma fa parte della famiglia Codemotion ed è anche parte del Manning User Group, per cui offriamo ai nostri membri uno sconto del 36% sul catalogo Manning e come membri della galassia Codemotion Aperitech offriamo sconti per le conferenze. E come ogni mese c'è l'estrazione di 2 ebook gratuiti su catalogo Manning che verrà fatta più tardi, sempre con un po' di ritardo, però alla fine avviene, abbiate fiducia. E nulla, questa sera l'evento sarà in inglese, per cui io farò lo switch in inglese tra poco e questi sono i nostri contatti e come vedete ci sono Twitter dove spesso comunichiamo i vari eventi, c'è una chat in condivisione con CodeGarden dove postiamo spesso link a nuove risorse e poi c'è il canale YouTube, quello su cui siete già, in cui è possibile rivedere i passati eventi. I will now switch to English to present the speaker from today, Leo from Graphistry. Leo, you're on mute right now. Okay. So he will introduce us to the magic word of GPU analytics. And I have nothing more to add probably. So I will let you the stage and we'll share the screen. Can I add your screen?
Yeah, I think the slides should be up.
Okay. As usual, I will just get off the screen in a second. As usual, if you have questions, just write on the YouTube box and I will read to Leo your questions later on. So said that, the stage is all yours, Leo.
Excellent. Thanks, Marco. And yeah, just as a housekeeping thing, I'd love to be very interactive in talks. This is going to be a lot of demos from a couple of use cases that we've been spending a lot of time on. So, but I'm gonna go over a lot of interesting technical stuff and a lot of tools. And so, if you have any questions, just I think there's most folks are going to be coming in through the YouTube. So just put in the question there, and then Marco will say something, and then I'll try to pick it up. And also, I should note, for the stuff you're seeing today, you can just go to graphistry.com, go to Graphistry Hub and just try it for yourself, especially if you do things like Jupyter Notebooks. Today we're going to be talking about looking at identity data using graph and GPU analytics. And so we're going to go through a couple of different examples. I want to look at it both from the use case side and how we kind of work through that, and then also you'll be seeing the different general techniques and then some of the specific technologies used to achieve those techniques. So there should be a little bit of something for everybody. So there should be some new things there. But before we go in, I would actually just like to say at a high note, I was just chatting with Marco right ahead of time. It's fun to be chatting with this group in particular. where we were chatting that Europe has always had a strong presence in the graph community around the world. I think like Neo4j is one of the I think it's now officially top 20 graph database, top 20 general database for the first time. And then for Italy in particular, we were chatting. I think the co-founder of OrientDB is from over there. The GraphAware folks have an office in somewhere in Italy. So it's cool to be with everyone here. Okay, so let's get started here. So the phrase data is interesting, where it's a phrase that I've actually personally started using recently, but I think it captures a lot of what we've been doing for a long time, and a lot of use cases that I think a lot of folks here probably see in their work. Even if you're not directly doing graph computing, maybe you're doing sales, maybe you're doing fraud, who knows, IT, even biology. The interesting thing with identity data is that it's something that touches on basically anybody. Maybe you have devices, or you have lots of users, and those are generating logs. Maybe you're running a website, and people are going to those websites, and they're generating logs that you want to understand. Or maybe you have some sort of scientific equipment, and you're monitoring some proteins, and you're getting kind of scans of what those are doing over time. And so basically, having that structured data over time is just such a general concept for any data analysis. And what I like to kind of joke is like Matrix sort of had it wrong and had it right. So you're seeing this photo here. They viewed the world as, if you remember the movie, they had the cool 0-1 binary view, and they viewed the world as sort of made out of ones and zeros. So I do actually think of the world as having a digital replica in the computer. But the interesting thing to me is not actually the ones and zeros for like you have a person with a cell phone. Like, I don't really think of that person as ones and zeros, but I do think of that cell phone as generating lots of logs, or any interaction that person's doing is generating lots of logs. And that's the digital view of the world. And so when we talk about identity data, that's actually, to me, almost about talking about understanding the world. Like, who are all these events? Who are all these entities, and how do we understand them through the emitted events, connect them all together? And once we understand that, and we can model that, then we can answer all sorts of interesting questions. Like, for any entity, what's kind of the scope around it in terms of what's going on? What's the history of it? Where was it? Where is it going? If something changes with that entity, like, or take some action, what's that sort of the blast radius? Are there any patterns or outliers? And so if we can get a handle on that identity data, there's just so much we can do. So that was really abstract and a lot of philosophy. And so most of the talk is actually going to be very concrete. And so I want to mostly talk about two examples of working with identity data. These are actually both from sort of our Data for Good effort, where we try to do some, or Graph for Good, as Neo4j calls it, where we just help some kind of nonprofit type projects. So the first one, we're going to be looking at human trafficking, looking at digital clues around organized activity. This is actually very similar to what a lot of like government teams do, and a lot of actually anti-fraud teams do, very similar. And we'll be using Splunk for that. And that'll, I think, be interesting both from the modeling perspective and from using GPUs. And then we're also going to look at COVID medical misinformation, which is a project I've actually been spending a lot of time on, and how we're using, I think looking at like Twitter is like a common thing for misinformation. That's kind of a known problem, especially also in Graph. But a little more interesting, I think, is how we're using things like machine learning to make fuzzy connections between different entities. And that's an interesting problem. Identity data is like that. How do you use machine learning to connect things? And in all of them, GPUs are going to be prominent. And then finally, I'm going to, at the end, going to try to talk about one or two new initiatives at Graphistry and some of that the GPU technology going on. So to have I realize maybe not everyone is familiar with Graphistry, so I did want to kind of briefly talk about two things here. One is we're generally, historically, we've been used more by advanced researchers and investigators, think like data scientists, folks using Jupyter notebooks. They could load in, connect to whatever data they have and explore it visually with a GPU accelerated graph visualization right from their browser. And maybe start doing automation, things like that. So we've been being used a lot by those folks for problems like security and fraud. Pretty cool. We haven't really talked a lot about this publicly much yet. We were actually recently awarded a Gartner Cool Vendor Award, so that was really satisfying. So after many years of working on GPUs to get that. A big shift is actually two things. One is for us, like folks are starting to realize what's going on with GPUs and graphs, and more broadly, not just with Graphistry, but some of the ecosystems we helped start. So Apache Arrow, they started getting, it's a way to deal with bigger data sets and represent that. So they've started to get awards and recognition. And then I'll talk about this at the end. Something called NVIDIA Rapids, which is kind of a part of ecosystem we help grow. They recently displaced Spark and Hadoop and a bunch of those kind of big data sets by using GPUs as an open source ecosystem. So we'll talk about that. And then for the Graphistry side, our job is to make this stuff easy. So you can just kind of connect to data and work with it. So you'll be seeing a bit of that. So okay, let's dive in. I want to start about the first case study. And inherent to it is this concept of, can we take records from the world, especially these log records, whether we the structured data over time, could we understand and work with it by using graph technology? And so I'm going to be talking about the Global Emancipation Network. This group runs actually a sequence of different campaigns, but a lot of them kind of have a similar pattern where basically they'll work on some type of data source, like maybe they're looking at criminal reports against businesses and trying to see patterns in that. Maybe they'll scrape legal records like that. The one we'll be looking at today is people working in a lot of criminal activity actually happens online and kind of semi-publicly. Often in normally used websites, there might be kind of like a lot of like a corner that does fraud or illicit behavior, things like that. And so we'll be talking about an example where they're looking at forum activity on web forums, and they're trying to see if there's a coordinated human trafficking type of activity. And so we'll take a look at that. So let's get started. Okay, so the Global Emancipation Network uses a lot of different technologies. For the database layer, they don't actually use a graph database. They use something called Splunk, which I'm guessing a bunch of folks here may be familiar with, but maybe not everybody. The idea with Splunk is it's really a log database where normally it's used by security and IT teams to just put whatever the machine is doing, their data centers are doing, they just dump the logs, and then all of a sudden you can just, as the logs come in, you can build dashboards and do search, and maybe you're familiar with Elasticsearch, you could do stuff like that. In the case of the Global Emancipation Network, this is a mock-up I did on an anonymized version of some of their data. For this campaign, what we're looking at is some essentially dark web forum posts where people are engaging some behavior, and we want to see kind of two types of questions. One is, could we do some sort of missing person type of analysis, where if there is a request, could we sort of see their timeline, and then kind of on the commercial world, you might talk about customer journey. Can we map out the journey of one user? Actually, missing persons analysis is not very far from that. Having a bunch of clues, can we get that journey? And then more from a kind of kind of making an impact more largely, we're also interested, could we see if there's a larger organized activity? And so if we could make that identity graph, are there kind of bigger buckets where some identities are more prominent than others? And so in this case, for example, let's say we're looking at one of the records, and then we're seeing there's a phone number for 236-1725. If I was going to do a tabular view, so how a lot of folks might start at the problem where they just load in all their structured data and then want to just do searches and dashboards, we'll see that if we search for that phone number, hit submit, that phone number was only active for a little while. And what's going on here is essentially sometimes maybe really just the person used the system for a while and left, but much more likely is it's a burner account. And so in identity data, it's very cheap to make a new address. It's cheap to make a new Twitter account, a new Instagram account. So people are often recycling those as soon as they get shut down. And so the question is, so we can't really directly search and get a hit. Like this one was only active for about maybe 1 month. But by using Graph, we might be able to go further. And so I'm gonna kind of walk you through that process. And so from an analyst perspective, what they want to do is say, hey, from my regular tabular dashboard, could I start at that phone number, but then can I get linked entities from across my different data systems? And so here we're going to jump into Graphistry. We're going to hit on that phone number. And I just ran all these like right before the talk, so this can be kind of semi-live. With Graphistry, we'll see that phone number, and we see that it's connected to a few Instagram accounts. Interestingly, one of those Instagram accounts, or a couple of them, seem to be linked to another phone number. And then if I kind of zoom out, we'll see there's actually, through that account sharing, through another Instagram account, we get to actually another phone number and another. So it looks like this particular phone number was indeed using essentially burner phones to kind of hide their presence. And you can see that instead of just having I think we were looking at May for the time period, we actually have a much longer time period as soon as we can hop out. Now, the reason I want to talk about this example is from more of like a data modeling perspective and kind of a modeling perspective both on the raw data and on the actual investigative workflow, like how we can use Graph to make both better. So let's break it down a little bit. So from an analyst perspective, again, like normally you just want to have that nice picture of, okay, from that phone number, can I see can I just somehow pull in all the linked entities and start to see if there's any kind of common thread? And so in this case, for example, once we brought in all the data, okay, we saw there was this account uses a lot of phones and a lot of Instagram accounts, so that's probably part of how they hide themselves. But we actually see that something in light blue here, there's a Telegram account, and that Telegram account is actually reused a lot. So even though this team has good operational security when they're trying to hide their identity, they actually have a weak link in their process. And so this Telegram account is actually a good indicator for who this person really is. And then as a kind of a cool trick when working with identity data and just basically event data with graphs in general, you'll notice that these edges have colors. And so time data, when we're doing any sort of real world analysis, actually ends up being very important. And so what we're doing here is we're actually, in Graphistry, you can make a histogram for any node or edge data. So one of the columns, so if for any of our events, we always have like a timestamp. And so what we're doing here is actually when there's a log record linking any entities, we're actually coloring that log record by the time. And so, for example, when we're looking at that Telegram account that's getting reused, we're seeing that a full rainbow spectrum of colors here. And this is, as an analyst, this is really interesting because now I know if it's just one shade, like let's say it's all just green, then I knew that account was only being used for a little while for that kind of green time period. But because we have that full rainbow spectrum, we know it's been used for the full time period. And this ends up actually solving a lot of problems in practice for using time data with graphs, especially with these identity graphs, where we actually know how long, what sort of the temporal pattern for that identity is. And we can just look at it and see. So this ends up being, combined with the normal interactions, like time bars and things, ends up being pretty powerful. So I did want to talk about the modeling, and I'm going to kind of go one layer, actually 2 layers down on what's going on there. So first thing, let's walk a little more carefully through how this analysis worked. especially given that we're actually not using a graph database. We're actually using a graph tool hooked into a non-graph database. So in this case, if we this is more kind of like an authoring view for how we create automations for modeling and working through these. Let's make the node a little bit bigger. So the idea is, as soon as we have a input, let's say like that phone number, we want to start generating queries against our different data sources, and then pulling those in, and then having them kind of modeled out. So first, this might I think this might be a term some folks know, some might not. So this already brings in the notion of a virtual graph. So what that gets at is we're kind of viewing the entire world, like all your databases and all the entities in those is forming like the general graph, and then what we're seeing on screen is sort of these pieces that are kind of loaded in. So it's kind of this virtual graph that's just really a subgraph of part of that broader graph. And so behind the scenes, we're generating queries on the left here that pull those in for us. And so, for example, when we have that 236 phone number, that's actually behind the scenes a Splunk search, which again, think like an Elasticsearch or like a Google search, just like a sloppy search, was actually run, and then the hits were brought in. And so in this case, for example, let's make it a bit bigger. From that phone number, we saw in red a whole bunch of these different data were hit. Each one of them had a bunch of metadata. And so from each one of those search results from that red row, we then, Graphistry will then look at the entities in that search and then put them on screen. So it looks like here we have like a lot of them, for example, in yellow mention New York. And so it's a bit bigger. We're seeing this case, this looks like some sort of longitude number position. And so a bunch of them were actually with that, a lot of the forum posts with that phone number were actually all had that same longitude position. And so what's kind of cool is, and one last thing here just on the modeling note, this sort of now underneath what this basically means is we now have a bigraph between events, like these rows, and then so each line here events, and then in between those, from each of those events, we extract different kinds of entities. Here I'm coloring the phones, states, things like that, different colors. And so we have this bigraph between events and the entities in them. And then I can always, so if I ever have a linkage between two things, I could always just click on the edge to see the event data. Likewise, if I have any entity, I can always see which events brought it in, or conversely, from any event, which entities brought it in. And then now that means I think about time, I could think about events, I could think about entities. This is good for authoring. Likewise, I'm able to kind of create not just a single search, but I can actually now start chaining together search commands. Like, can I go from a phone number to a social media account to some web pages, things like that. So I can think about both about modeling my data, but also modeling my workflow, and kind of making that, if we go back to that use case, could we go from a phone number to a multi-step investigation across multiple or multiple tables across one database. But again, when I'm actually in the heat of the moment doing the investigation, I just want to click on a phone number and get it mapped out. So this is a very zoomed in view of what's going on, how we're able to get the given one entity or one identity and kind of get that journey around it. I want to share one more thing about that use case that I found pretty fascinating. So the below was just was already the Graphistry platform doing normal graph investigation workflows using these graphs. We call them hypergraphs. Don't want to get into that now. But there's an interesting thing that sometimes when we're working with identity data, sometimes there's stronger patterns. And this is where one of the areas where GPUs come in. And so I want to share here, if we're looking at another identity, what's a good way of saying this? Sometimes like we just want to look at one actor and kind of look at it, but sometimes a lot of the important stuff is bigger and more coordinated behavior. So maybe we're doing fraud, and then there's a bot network that's doing a lot of the disruption to a service. Maybe we're doing customer analysis, and there's a big customer cohort that has some interesting commonalities. And so sometimes what we really want to do is to, instead of being very zoomed in, we actually want to zoom out and get more of the big picture. And so in this case, for example, we're looking at the same data set, but now we're going to load in about 74,000 entities and 100,000 connections between them. And then what's kind of cool, I'm just playing a video here I had loaded ahead of time, is that Graphistry uses GPUs where it can actually see the full picture. Let me pause this in a second. Here. Okay. So what's kind of cool is that on the front end, we were actually able to load in a bigger chunk of the graph without crashing the browser. So this is actually a medium-sized data set for us. We're showing about 100,000 edges. But if you want to throw like 1 million edges onto your screen, Graphistry can handle that. So we're one of the only web tools that can. And why that gets interesting is that if we're looking at this identity graph, we actually see there's some hot spots. And keep in mind, this is a case where we're looking at potentially criminal activity around human trafficking. And so if we have somebody who's doing a lot of burner phones, that's really strange, especially if we're associating that person with trafficking multiple people. If I was doing an enforcement approach, these are the hot spots where probably the most people are getting, like somebody's treating this not as some small thing, but actually as a operationally heavy, busy business I'm going to look at. Or if I was looking at, let's say, botnets or fraud, again, these are the network. And then we can kind of then zoom back into operational practice. I do want to make one technical note here on the use of GPUs. On the front end, we're using them sort of like a video game where you can pan and zoom and you're seeing that. Where we're actually also using GPUs in the data center, and this will be noticeable much more in the next example, but we're using GPUs in the data center so that if we want to do real-time clustering, real-time filtering, we don't actually have to send gigabytes of data into the browser. We can actually keep that interactive by sort of like Google Maps or Netflix connecting to your GPU cluster in the data center. So we're the only graph platform that works that way. So that ends up enabling your visual investigations in a pretty cool way. So let's jump back to the top for a bit. So that was for that first use case. So hopefully what you're getting a little bit about was this concept of where virtual graph and hypergraphs come in, especially in identity data. Also a little bit about the GPU scale, and then more subtle is about how do you actually do the automation. So hopefully those are techniques for working with identity data that should resonate. Okay, so for the next demo, this is a pattern that's we're seeing a lot more, starting to happen a lot more in more advanced teams, and I think this will be over the next few years the type of technique I'm going to be showing you here. We're going to be seeing this start to get picked up by more broadly by other folks. And for the use case here, what we're going to be talking about is medical misinformation. So let me step back. So the scenario I want to talk about, like technically, is about given a graph, can we infer linkages? So if we have a bunch of identities in our graph, maybe they're mislabeled, maybe they're different aspects, like a phone number versus social media account. Maybe they're bots controlled by the same person. But could we infer that even if the raw data didn't have reuse, could we infer that they're somehow connected and make fuzzy links across identities? So I think technically that's going to be more and more important as graph gets more popular and just data becomes more heavy and we have more of this identity data to work with. And I want to talk about a use case. So I'll talk about a workflow we do with that. But the use case I want to talk through here is a project I've been heavily involved in, which is projectdomino.org, where we're trying to build anti-misinformation AI technologies for community leaders. And so imagine, so one of the things we do, for example, is we just, anytime somebody talks about COVID on Twitter, we're actually ingesting that and trying to drive that through various models and detections. So for that use case, I'm going to set it up a little bit more. When we're monitoring COVID tweet activity, that's somewhere between 100,000 to 1 million tweets a day. I forgot the exact number. It's just, it's a problem for everybody. Italy, obviously was one of the first countries really hurt by it. And in the US, it continues to be a massive problem. So just everyone's talking about it. And I was just reading today, the vaccines in the US, for example, aren't going to be ready for the broader population probably until at the earliest somewhere around May or June. So it's going to be, until then, one of the most important ways for us to act on it is understanding and influencing public behavior, like are people wearing masks, or they're washing hands, things like that. So that's kind of why we understand the people who are sort of trying to undermine public health. The infrastructure setup is pretty usual. So we stream in the tweets, we drop it into a Neo4j database, and we'll do things like, for example, there's like a node for users. Those users might have be connected to the COVID tweets they're doing, and then sometimes they might try to share information with one another about what's going on, maybe a joke, whatever, so various URLs. And what we're interested in at Project Domino is when there's might be misinformation URLs, like of known bad URLs being shared, and then there might be communities or trolls, things like folks like that, trying to intentionally share it, or maybe they're folks who are kind of have been tricked or sort of radicalized and then are resharing it. So we want to understand that stuff. And where it gets tricky is sometimes it's benign, where it's just an organic community doing things, but sometimes people are creating bots, and those bots are just doing sort of very mechanical, behind the scenes, automated actions to promote concepts. And those often don't follow normal social structure. And so the unintuitive thing about doing this analysis is we might have, let's say, if somebody's running a campaign with like 1,000 bots, each bot might not actually be friends. They may never mention each other on Twitter, and so there's no direct connection using account names or anything. They're like, from the normal Twitter graph, the bots are not connected. But using machine learning and looking at the content, we can actually infer the connections. And so that's what I want to talk about. And the way we do it, we actually use a technique that Graphistry has been using on a lot of different investigations. So I'm going to kind of go through that. So it's interesting in a few ways. So the investigation team, folks are probably, some folks are probably familiar with something called Jupyter Notebooks, maybe not everybody, but it's a way that if people are a little comfortable with Python, so this is more for advanced analysts, they could share their investigations, and those investigations could connect databases, they can do like SQL, and then they could inline different analytic results. In this case, for example, I think we wanted to understand if there's a bunch of medical misinformation campaigns, or I guess for this one, just general misinformation campaigns. To do SQL, we were able to do a cipher query against Neo4j just to pull in a bunch of those tweets with using a bunch of hashtags we're curious about. And then we wanted to start inferring connections between those tweets based on their text content. So I'm going to show it explain what's going on in a few steps, a little more visual. So the first thing is, like, for each user account we're looking at, some of them we're talking about like known misinformation campaigns. And so we were just kind of here, like, for example, mole children. So mole, if you're not familiar with the English term, a mole is like a little animal, and so mole children is like a child who's, I can't even explain this. But some of the accounts, we're talking about the known conspiracy theory about mole children. And so for any account that talks about mole children, we'll just kind of have a count of how many times it mentions it. And so for across all these different conspiracies that we were kind of looking at, we were able to kind of sort of get a fingerprint for each account, like how active like maybe 10% of the time it talks about mole children, and then 20% of the time it talks about COVID, something like that. And so we now, for every account, we sort of have this fingerprint. And so now our question is, from those fingerprints, can we start to realize maybe some of those accounts are either ideologically similar, or more likely they're kind of the same person controlling the bot and using it across multiple campaigns. And so I want to take a look at how we do that. So what we're looking at here is we ran those we just from Neo4j we were able to load all that data. Like I forgot, it was like 1 million, like 10 million, whatever tweets around these topics. We were able to just kind of compute that table of labeling each account, summarizing each account based on what it's talking about. Then we ran it through something called UMAP. So UMAP is a dimensionality reduction cluster algorithm. That's a really fancy way of just saying for all of these different tags, could we just use the algorithm to reduce it to an X and Y position? So for every account, could the algorithm just kind of cluster it and put it in a different position? And so, for example, over here we have a bunch of China-related accounts where they're only talking about a certain Chinese term. And so we have all the counts sort of kind of clustered out. And most traditional machine learning works this way. It just takes a table and then lets you kind of classify them, maybe dimensionality reduce them into an X and Y, something like that. Where it gets interesting from a graph perspective is now what the machine learning has kind of told us is that maybe these accounts are kind of connected somehow. They are a little different. They're not put in the exact same place, but they are kind of similar. Like maybe one talks a little bit more about mole children than the other. But either way, as soon as they're kind of next to each other, what we can start to do is we can actually add links between them. And so let me kind of draw those on screen. And so we can start to link them together. And that actually forms, so now what we have is our Twitter account graph, but it's, the linkages are not based on somebody retweeting one another or being a friend, but actually by having a similar fingerprint and using the algorithm to connect them. And all these notebooks are public. Where I wanted to go with that is once we have those linkages, we can actually start doing analysis of that identity data in a much richer way than kind of we might traditionally. So in this case, something I did was, did a couple of things actually. What I did here was I announced for each one of those accounts, I colored it by how often it talks about QAnon. So QAnon is a particular conspiracy group or misinformation group that I guess publicly has been more in the news after we started doing this analysis. But we're seeing, for example, for this cluster of accounts that some of the accounts often talk about QAnon, others don't. But overall, once you actually look across all of the conspiracies, even though these talk about QAnon explicitly more than those, they actually talk in terms of that fingerprint. For the other things they talk about, they actually talk about in similar weights. And so that really, this kind of fun cluster where we kind of see, it probably is QAnon folks, but even if they're not always outwardly so, but behaviorally similarly. Likewise, what we're seeing is beyond just using that not just to understand that this might be one or two different identities that might be actually the same person running two different accounts. We actually also understand this from almost a demographic or cohort perspective, where a lot of misinformation works through campaigns. And so the question is, are there different campaigns going on, and can we start analyzing those? And you're starting to see there's actually different structure to those different campaigns, where each campaign might involve maybe multiple bots who are acting in a certain way, or maybe they're successful and normal folks pick them up and then they interact with it in different ways. And once we link those identities together using the algorithm, we actually start to see a lot of interesting shapes. And so this broader workflow of, actually, let me step back. So this already is giving us a nice canvas of what's going on with that identity data. And so just basic search techniques let us zero in on 5,000 accounts. But once we ran the algorithms, we're able to infer about 100,000 connections between them, which is what you're seeing on screen. And then by using GPUs, we can both interact with it visually. But here, for example, I'm running the clustering algorithm. It's actually running the clustering on the data center and streaming the result in. Now, me as an analyst, I can actually interact with this data and explore it. And so the Domino team is actually a bunch of folks. And they have different specialties. Some people are coders, some are data engineers, some are data scientists, and some are just more like analysts who need more point and click tools. And so this has been very important to be able to create flows like this where we can just generate these and let people start investigating and, like, hey, what is this hotspot over here? What is this topic? What are these accounts? And enable them to do that. Let me jump back here. So I want to be, for folks more on the data side of things, I do want to be clear about that workflow that we did here. This is a pattern we've been seeing in cross projects, where sometimes there's a custom algorithm to do the linkages, but very often what we actually do is something called UMAP. So look it up. It's they're both CPU and GPU versions. I'll talk about the GPU in a second. But basically, we'll run UMAP on that table of data. It'll reduce things to X and Y positions. Then we just use nearest neighbors. If things are kind of clustered near each other, we'll just kind of make those fuzzy links. And once we have those fuzzy links, then we could bring them into a tool like Graphistry to do regular graph analytics to understand what's going on. And so we've done this for fraud, we've done this for genetics, we've done this for, you were just seeing this on the misinformation analysis. It's become a very important part of our workflow. So that I want to talk a little bit about underneath what's going on. Actually, yeah, and so GPUs have been an important part of that. So in the first demo, you saw that we were able to kind of show like hundreds of thousands of things on screen, zoom in, zoom out, and that worked. And the second example, when we were actually able to do a lot of the machine learning and interactive analytics in real time, you saw me doing that on screen. And GPUs have been an important part of that. So I'm going to talk a little bit about that, both as a general technology and also as something that I encourage anyone doing graph tools to start using, whether through Graphistry or some of the partners that we're working with. So first thing, GPUs may not be the most familiar thing to everybody. You know, they exist, but maybe not why they work so well. Two comments on that. So the first thing is like, why GPU versus CPU? Like, how does that, like, why is one working and the other's not? And I'm gonna kind of show this chart first. So one is so this chart, what we looked at is the cost of GPUs on Amazon and how much how much performance, like how many floating point operations per second you get for like $1 on Amazon. And the second is how many gigabytes of RAM on those GPUs you're getting. And so over the last 10 years, we've gone from like, 0.5 teraflops a second per dollar to now about 15. So this is about a 30x over 10 years. GPUs, the performance per dollar has gone up about 30x. And so if you remember Moore's law, which is about the doubling, this gives us a nice doubling over the last 10 years, and it's actually pretty steady. Likewise, a nice analog, especially when we're doing data-intensive workloads like graph and machine learning, you actually want to store more and more of that data in GPU memory, so it doesn't you don't have to go fetch it to the network or swap it in or out. So kind of like how Spark replaced Hadoop by keeping data in memory, you want to do the same thing with GPUs as much as you can. And you're seeing over those last 10 years, we've likewise had a nice growth in available memory per GPU. And so Moore's law, if you, it was great for the CPU era up till what was like 2000, 2010. But for now, in terms of how much computer memory you get per dollar for CPU, that's been, or actually really like the performance, that's sort of flatlined. But with GPUs, it's actually for the last 10 years. At first, is more expensive, but it's finally it's finally at the point where it's growing at a level that the CPU stuff just can't keep up. So for whatever workload, at some point, it will be more effective per dollar than the CPU equivalent. For a lot of what we do, it's been there for a year or two. So this was fun. Now, the intuition I did want to say is basically on the CPU, what's going on is they'll do things like speculative execution, like smart if statements, like all these fancy silicon. So if you have one thread, it's throwing all the silicon, all this power just to make one thread like maybe 5%, 10% smarter. And then you kind of get diminishing returns for how much intelligence a CPU puts in. While GPU says, hey, we're gonna use all that same silicon, all that same power, but we're gonna be really dumb. But we're going to let you, if you have a bunch of threads. And so if you're smart about how you write the code and you do all that work to use all of those, you'll actually be able to leverage it. So instead of going 10% faster by having a bit more smarter branching, maybe you could go 10 times faster for that same silicon because you've actually already mapped it out. And so that's basically what's going on. But the problem is you need to be able to write that code. So Graphistry, this is stuff we use internally, but as you're seeing with stuff like the Jupyter notebooks, oftentimes somebody will be using us in a notebook. They'll actually use those tools and then send data to us and through it. And so a way to think about what's going on there is maybe, wow, 15 years ago, I feel a little old now. Hadoop became a big thing where we have distributed CPUs. And then 5 years later, Spark came out and said, hey, we'll have distributed CPUs, but if we keep data in memory, they'll go faster. And then the GPU people, maybe 5 years ago, they started realizing, hey, if we run some of those compute on GPUs, we'll have those benefits I just talked about. And then a few years ago in our community, we said, hey, well, actually, if you do your full data pipeline this way, you can actually run general workloads. You could parse data. You can do all that stuff you're doing in Hadoop and Spark, like load data, parse it, wrangle it, swizzle around, group by. Maybe sometimes you're doing machine learning, but maybe you're also doing all that other stuff. That all works there too. And a few years ago, we were doing it just for single GPU, but the communities come together around something called Rapids, which lets us do it across multiple GPUs. And so today, commonly, you might start with one GPU, and then maybe you have multiple GPUs on the same node, and then maybe you go to multi-node, multi-GPU. But either way, you're getting this all along. You're getting this kind of cost benefit and performance benefit. The reason I bring up Rapids is it's a Python framework that takes a lot of the tools you're familiar with. So for example, in the graph community, a lot of folks may be familiar with something called NetworkX, which is a CPU-based graph compute framework in Python. cuGraph is basically the same API. So you get to write your high-level Python code, but underneath, it's actually getting mapped to one or more GPUs. And so it ends up being able to do some really ridiculous workloads. As an interesting note here, the last year has been a bit of a shift in our community. So a lot of the work up to last year was mostly about just making this work at all, and especially in a single GPU setting where you might have 16 gigabytes of in-GPU memory, and if the workload's that size, can it work? But then over the last year, like now we're kind of getting those individual node pieces to work. The effort has now been to say, well, instead of dealing with 16 gigabytes of, imagine like log data, like your identity data in logs, like 16 gigabytes of logs, what happens when you have like a terabyte of logs? So we want to then do two things. One is maybe we can have multiple GPUs to keep them all in memory across those GPUs, but maybe also we can be smart about paging the data in and out so that even if I have one GPU, I can still deal with that 10 terabytes of data, even though it only has maybe 16 gigabytes of RAM. So that's something called out of core. And so a pretty big deal a couple months ago, maybe a few months ago now, was the official numbers started coming out for TPC-XBB. This is a really boring name for a really exciting thing. So TPC benchmarks are the databases communities for how they benchmark databases. So this is really the standard that folks agree on. And the big bench is the one where they look at a couple of things. One is, could you do bigger data sets than might fit into RAM? So in this case, most of the workload, I think, is 10 terabytes. Though actually, you can actually put that into RAM nowadays. But one thing is it's interesting in the size. So it's way bigger than GPU memory. And the other thing is, like you're seeing here, 21 different benchmarks. There's actually all sorts of different tasks. So it's a very heterogeneous workload. Like you can't just do graph. You can't just do SQL. Like you have to really be able to handle a diverse type of workloads. And so for the Rapids folks, you're seeing that across queries. It might be for some of them, looks like they're not doing as well. Maybe by not doing as well, I mean it's 2 times more, half the cost or double the performance. But some of them, like an increasing chunk of them, we're seeing 70 to 100x. And these aren't naive implementations where like people are just writing something. This is like this is one of the battleground benchmarks. And so to show a 75x better performance or better cost that's a big deal, because this is really where Spark and Hadoop and everybody really fight it out. So that's a big deal. And the note I want to reinforce here is, as we're building out our stack, you're writing your Python or you're using Graphistry, you start getting like a knob here where maybe you don't care about your budget, you just want to go as fast as you can, and then for that time you just turn on multi-GPU, or maybe you do care about budget and you want to just do out of core. So let's say we only use one GPU, like maybe 30 cents an hour on Amazon, but because of the out of core, you can still do this for full workload, and you're still getting more performance than, say, with Spark or Hadoop for that same 30 cents an hour. So this was an interesting milestone here. So for Graphistry, I'm going to kind of show two things briefly here. So the first one is kind of following that timeline of Rapids. It's something that I was hoping we'd get out for the talk today, but it looks like it'll be bleeding into next week, is our ability to load in bigger data sets for individual graphs. So in May, we talked about, we wrote a little blog post on how we're able to load in about data about 10 times faster, or 100 times bigger than we normally worked with, by using some of these Rapids technologies. And so we posted some benchmarks where, these are things that you might have to run for hours on Neo4j, or like you would just crash Gephi. But here we were able to just in less than a second or 1 or 2 seconds load in 100 million rows, and it was fine. What was kind of exciting is now with that multi-GPU or out-of-core stuff that we're starting to add, that means we can, beyond just doing these gigabytes of data, we can now load in, we're trying to work on, can you do 10 billion rows of data and have really big graphs and things like that. So again, stay tuned next week. I was hoping a demo, but you'll be able to see that next week. The last thing I wanted to show here about making this stuff easy to use, this is actually going back to Project Domino. A big part of Project Domino of supporting that team is to enable different people on the team to do graph. And so at the very last step, we do get a visualization that an analyst can kind of point and click with and do time bars and kind of, they don't really have to write code on. One aspect of that that's very important for enabling a team is actually the ability to create dashboard tools. And we found that the dashboarding ecosystem for the graph community has been not really at the level that we're seeing in the data science community and the broader BI community. And so I want to make a quick point to a project that, again, I've been working on this one, something called Graph App Kit, which is related to something called Streamlit. So Streamlit is basically, if you could do Python notebooks, you could do Streamlit dashboards. It's basically the same thing. I encourage you to check out this project, Graph App Kit. But basically, instead of just having the Graphistry views, you can actually start doing these little dashboard panes. So particular something to check out here is we have some, we already put up the Neptune launcher. So Amazon Neptune is a graph database from Amazon. But basically, you could one-click launch an Amazon Neptune graph database, and then you can one-click launch Graphistry plus the Streamlit dashboarding using the Graph App Kit, which sort of has all the batteries included glue between all this stuff. But once you one-click launch those, what you then get is like a full dashboarding environment where you can do public dashboards, you can do private dashboards. Neptune is based on Gremlin, and so you could basically very quickly go from adding a little slider for, let's say, we actually have an identity demo here. So a slider on which country you want to look at for your identity data, generate that Gremlin query, and then get the result back as one of these Graphistry visualizations. So I'm looking at the time here. I think this is roughly where we want to end here. But I encourage you, if you're into any of this stuff, drop by our Slack channel, follow our Slack, stuff like that. Yeah, drop by our Slack channel, ask questions. And then also go to Graphistry Hub. Show here. So if you go to, you can run this stuff in your private data center, so you can launch your own private server. But if you're just getting started, you can go to something called Graphistry Hub. So we our own for public data. You can kind of get your own Graphistry account, and then you can try doing it from your own Jupyter notebooks, things like that. Or if you do want to do the private data stuff, a fun approach is actually just doing the one-click launch and getting your own stack. And just hit me up on Twitter or on Slack, and can kind of introduce you to the community and guide you through building your own dashboards. So that was a lot of stuff. Hopefully there's some kind of new things here for you. So again, hopefully you got a bit about the how we think about things like log data and identity data, like from the kind of the fraud and trafficking examples, or more from the social data, like when we're looking at like the Twitter misinformation, both like when it's like the data is directly in the graph, or it's when we have to do machine learning to pull out those relationships. But when we start actually making those, understanding those like those journeys and those patterns. Likewise, a lot of what we're doing is actually enabled. That was one of the core tenets of Graphistry, that we can actually 100x what we're doing with like more modern visualization with actual GPU acceleration, and start imbuing it with automation. These are all individually 100x technologies. And what was kind of exciting as part of our mission, we did want to engage with the not just have us build the point and click tools. We believe the open source was an important part of that kind of community. And so we're since the beginning of a lot of these GPU tools, we were right there contributing and helping those communities grow. And so if folks are developers, you can actually code some of that stuff yourself. You don't have to be a GPU coder. You can just do Python. And then once you do have that result, you can just plug it into a visual workflow like Graphistry that's kind of native to all this stuff. So wow, that was a lot of things. I'm gonna end it here. And again, go to just head over to Graphistry Hub if you want to try it for yourself. Try your own server, launch your own server, or get a free API account and play around. With that, I think Marco, I'm gonna turn it over back to you. I don't know if we have any questions here or anything, or if you have any questions. Or
oh, thanks a lot for your talk. That's been really insightful on the actually your use cases. Quite, I was expecting something more specific, but it looks like you span quite a lot on these identity investigations from well, different aspects in general. I mean, it's really attacking this identity investigation from multiple fronts, it looks like. There are already a couple of questions I can direct to you. One is from Simone. He's asking, with your version of the force directed layouts, what is the maximum number of nodes and edges that Graphistry can handle, guaranteeing rendering at least at 15 frames per second?
Yeah. So short answer, we kind of like doing maybe at most, I don't know, for slow versions, maybe 1 or 2 million edges, and then maybe 500,000 nodes. In practice, I like to keep it about maybe 100,000 nodes and maybe a few 100,000 edges. What's interesting about it is, remember, we have a client server set up. So think like Netflix or Google Maps. So the front end, if you've already loaded in all the data and I'm just panning and zooming, you can actually do that you can actually have that full thing in there, like the million edges, and it's fine. When you're actually doing the real-time clustering, we're actually doing that in the data center. Today, and so there are 2 bottlenecks. You have the compute and you have the network. Very often, it's like bound by actually your network connection. I have a terrible network connection here. One of the joys of being in America. So actually, I'll actually have smaller graphs, just not because of the algorithm, but actually because of the network speed. But if you're at a company, for example, or a government group, you're actually inside of you might have like 10 megabytes a second or 100 megabyte a second connection. Maybe you're in a civilized place and they have a gigabyte connection, and it just flies. Or maybe you have an analyst workstation. The other part there was what we're working with on that multi-GPU and stuff like that. There, we're actually trying to get to the point, could we do, like a gigabyte, 10 gigabytes a second? So that's already, like, that's starting to change what's possible entirely. Though we're focusing there less on the clustering and more on like filtering and things like that, and group buys, stuff like that.
So that, if I understood correctly, your architecture is basically visualizing as the picture you can pan and zoom like in Google Maps very quickly, while for heavy computational task, you just move. I mean, you're performing this task on the server. Are those servers a public cloud, or can be hosted on a hybrid or private cloud as well?
Yeah, so we Graphistry Hub, that's just, we run some GPU servers for folks. So that there you can just go get an account. You don't need your own GPU. We'll do that. We actually, a big focus on us is we're gonna be launching a lot more stuff there over the next year. And you don't have to worry about GPUs that way. That quick launch button you saw, that actually lets you run your, just one click and you launch, and in Amazon and Azure, you'll run your own Graphistry instance in your own private cloud, so we don't need to see your data, and you can keep everything private. For enterprise folks, it's just Docker. So we spend a lot of time making it. Docker's not one click exactly, but because we were able to we were careful to roll up our stack, you just Docker compose up, and you have a Graphistry GPU server.
Okay. Okay, seems easy on both sides. Piero is asking, well, it's quite a general question, but I would like to build on top of that. So he's asking, can you please elaborate on the machine learning aspect? It's quite general as a question, so probably I have a couple of specific things I may build upon, and maybe you can start to answer these, and then we'll see where it goes. I mean, you presented the linkage system built on top of AI using UMAP and KNN. Is it, in your experience, a solution that it's proven to work, or does it? I mean, looking at the charts, of course, it works. It's everything perfect and well positioned, and but all those small clusters or even bigger ones, I noticed there is quite a full mesh kind of pattern. So my question is this technique proven to work, or does it generate too much noise to actually be practical?
Yeah, so something like UMAP, for example, in cancer genomics, let me step back. So the UMAP technique in particular is actually several algorithms deep. So folks used to use k-means for dimensionality reductions. That's kind of one of those introductory ML algorithms. Then something called TSNE came out, which was sort of a bit better. That became, folks like in cancer genomics started using it. And then Leland, I apologize if you're watching this, I never pronounce your last name, but Leland did really great work with the UMAP algorithm over the last year or two that's sort of getting replaced, starting to replace most uses of TSNE, and basically in all our workloads it's replaced it. We use the GPU version via Rapids, and I would recommend, as long as that fits, that should be the one. Generally, UMAP is used for the exploratory part of the analysis. Folks in genetics and stuff, they have just so much data that they actually build classifiers and stuff on it. In our experience, as soon as you start understanding the domain, we use the UMAP to kind of map out, and then if the problem merits spending months and months of model building, like custom model building, then we'll switch from the UMAP to something more custom built. But generally, most problems in our experience do not merit spending that much time and money. So we actually, in practice, basically, UMAP is one of the first things I always reach for.
Okay, that's interesting. On the same wavelengths, you kind of answered that. So I was curious about using UMAP as a graph layout. I always thought about that. I did some experiments, But I think the missing bits was actually the linkage, which you you introduced with that. Still on the linkage, what about the overtime? I mean, all the use case you've shown is basically a time frame snapshot where you run your algorithms and then you have all the linkage. What about evolution over time? How do you handle that?
Yeah, so the first, so there are kind of two things going on. One is just how do we work with time data, and then the second is what's the deal with UMAP and time data. So that first case study where we're looking at the human trafficking and with the digital trails, I kind of was showing, just for most investigations, actually just being able to see time, and instead of just having a time bar, so like a lot of tools will just give you that time bar, being able to do coloring based on time and making that very fluid, being able to kind of go in and out. That's actually a lot of times the most important thing we do. For the UMAP side, if we step back a bit about like what's going on, there's kind of two types of data. There's traditional graphs are involved with something called categorical data, where we might have like a very concrete items, like we might have like an IP address or a username or a bank account number or a phone number, a file name. Those are categoricals. Like you can have like the category of files and with all those distinct names in there, and then we might have links to connect them together. While something like time is a continuous variable. But just as like time, we might have score, we might have age, we might have, if we're doing a blood test, we might have like, I don't know, cholesterol. I think you can get cholesterol from the blood level. I don't know, I'm making it up. But you have lab values. These are all continuous variables. They're in like 0 to 1 or whatever, like very smooth. Something like a UMAP is about doing clustering on these smooth surfaces. So they come from the topology world, or they're topology inspired. They're about if you have a lot of these high dimensional smooth things and we believe there's a structure behind them, can we sort of interpolate and pull those out? Well, a lot of the graph world has came out of the more of that categorical, like can connect things. And so I didn't explain it this way when I was showing it, but you kind of hit into that problem when you were trying to figure out like, when do I do graph, when do I do UMAP? There are actually two different types of correlation problems. One is for these smooth dimensions, while graph is historically for these kind of categorical name-based ones. And then what I showed in that example is like, well, if we have those entities of interest or that metadata, sometimes the edges could come from the normal graph because we've linked them directly in the data, but sometimes the connections could come from doing smooth modeling from something like a traditional machine learning world on on continuous data. And by putting both types of edges into the graph context, then we can actually work with both kinds of data together. And so that's actually, it doesn't need to be UMAP, it could be anything else. And that's pretty ridiculous, actually. So this is where I think graph is going to be very important in the coming years, like knowledge graph, things like that.
Okay, that was quite an interesting answer. I hope Piero has been satisfied with your insight in that.
Oh, sorry, I want to add one thing. So you asked about change of networking things. So the reason I want to I answer that question that way is change is sort of a time dimension. Like maybe an edge exists for a while, but then it stops existing. So that's something that UMAP can actually handle. Is like, is it seeing those samples and later it's not? That's a pattern that UMAP is like. That's a pattern on the continuous dimension. And so by being able to have those linkages there, that now becomes something as part of the UMAP's contribution to the analysis. The next level of that is there's notions of kind of graph fingerprinting, which is used in graph neural networks. And so I'd recommend taking a look at kind of topological or categorical descriptions of how graph neural networks do what they do. And I think that's going to be the next level of what's going on there. So dynamic graph networks via graph neural networks. But even there, I get out of my league at that point, but it's interesting.
Okay, that's okay. So that's the topic for next year, for next talk.
maybe 3 years.
Okay, fair enough. I don't see any new question, although I have a last one. You shown before the Moore's law charts for GPUs, and it all makes sense. Although if you can show it back, I wonder what's going on in 2017. I mean, your lines are perfectly straight up, and then there is those on the right-hand side. Yeah, on that chart, there are those points which just are off for the.
Yeah.
Yeah.
So keep in mind, this is, in one sense, this is the most real numbers you can have. These are the market numbers of actual what you can get public cloud. This is a commodity, you know, all the hijinks after. But at the same time, these are, in reality, there's only really, there are multiple companies who make GPUs, but in practice, it's NVIDIA. And then likewise, when Amazon launched GPUs in the cloud, the first time they were actually releasing was actually somewhere in the middle of this time period. And in public cloud, for first couple of years, it's only really Amazon who had them. So Google and Azure were slow. And so we had a world where you had sort of one company who, like on NVIDIA's side, they had like, you know, the Bitcoin stuff going on, all this video game stuff going on. And so, and they were actually new to using GPUs for machine learning. They're mostly used for games at that point in time. So they were they had their own political problems going on, and they're figuring out their market stuff. And then Amazon had this monopoly on GPUs in the cloud, right? So all that, in my opinion, actually, a lot of these prices were artificial, like artificially high due to monopoly and political scenarios. And so I actually expect these numbers to actually keep going, and part of it just because there's so much weird political and corporate margin that that now is starting to more utilization based, I'll put it.
Okay. Yeah, I guess the how's it called, that Google, it has a sort of Jupyter network, sorry, a Jupyter notebook version Google, which is using GPU from their own cloud, I think. Is it? Cool. This is okay. Did it start around that time, probably 2017, 2018, I think.
Exactly.
So, okay.
And everybody should use it if you haven't. It's amazing.
Yeah, definitely. Yeah, it's definitely incredible. Now, I think Azure has one similar tool as well, but yeah, I think I use it once. Okay, so I don't see any new questions. I want to ask, well, thank you for your talk, and I mean, to present today your solution. That's been really interesting, and well, next week we will sync on the, we will go on your website and see your new solution, the 100 times faster. So Graphistry version, right?
Yeah, we're gonna. So the big thing there is actually for a lot of what I showed today, you might need to write a bit of Python code. So like if you're familiar with Pandas data frames, things like that, it's native to that stuff. We're finally, what's actually really launching next week is point and click. So you can actually just drop in a big file, and they'll be able to load it in, and you don't have to do any of this stuff. Like it'll just work. So that's been it's been exciting.
Okay. Okay. So yeah, I guess we want to thank you again for the availability for today, and say we end up the webinar. So.
Great. All right, thank you everyone, and again, stop by the Slack and try it out. I'm happy to help. So a lot of this stuff is really fun, and a lot has been changing. So be curious what folks are going to be up to. All right, well, thank you everyone.
Okay, bye.